he actually, his work is related to what I'm going to talk about. I didn't know for a long time, actually, until maybe a couple of weeks ago, that in fact, he was a teacher, in fact, the advisor of Anthony Zygmunt. So, just wanted to mention that. Also, I make up the slides to my taste, and I really like to see ahead of time how much I have to, well, I can say endure, right? So on the left, here you can always see how far we are, but I also have a plan. Okay, it's not working immediately. Why not? Huh? Yeah. Thanks. Okay, so now it's working. And it's not working. Why not? Do I have to push something here? Yeah. So this is just basically a table of contents. And it is in more details what you see on the left. So it looks quite a lot, but I broke up the material into small parts. So hopefully it's not going to be, I mean, it will be manageable. And so let's start with some reminders. So the mean ergodic theorem, which I will abbreviate as MET. So in a dynamical system, XMT, where M is the measure and T is the measure preserving transformation, and F in L2, the limit of the ergodic averages, the usual ergodic averages, converge to the invariant projection of F here. So I'm using this notation for average. So this is an average of a sequence Fn, and it just means this exactly. And here, whenever you see an interval, it means an interval of integers. So that's how you should look at that. And more generally, we will see it only once. Whenever you see some kind of finite set here in the index part in a subscript, that means that we are averaging over that finite set. Okay, so we are normalizing by that. So I just want to mention that. And we know that by the spectral theorem, using Weis notation, this one, so E of theta is equal to E to the 2 pi I theta. The mean ergodic theorem is a consequence of the limit of the averages of E and alpha existing for every real alpha. And also, since we are talking about, in fact, identificational limit as the projection of F onto the invariant sets. So this limit is equal to 0 if alpha is not an integer. And if alpha is an integer, then the limit is equal to 1. Now, we also talk about mean ergodic theorem along Odin sequences. For example, the squares, I just singled that one out here. So it just means that we look at the ergodic averages along the squares. So that's what you see here. Right, so the squares. And this is supposed to exist for every F in L2. By the spectral theorem, it is a consequence of again, similar averages of E and squared alpha for every alpha. That's very important. And this is again true by Weis result that the limit of these things exist. And we know that for irrational alpha, we have the same limit as in the classical mean ergodic theorem. So the limit of these, or the limit of this, is equal to 0 for irrational alpha, which is equivalent with uniform distribution. But for rational alpha, where we write alpha as A over Q in simplest terms or reduced terms, I forgot what the exact terminology is. So the GCD of A and Q is equal to 1. Then the limit, in fact, is equal to this. Sometimes, so you see that we are averaging over only in the interval 0Q. And this is sometimes zero, but rarely. And most of the time, in fact, it is non-zero. And it doesn't play any role in our talk, but the absolute value of this is about 1 over square root of Q. So just in case you want to know. And so let's see. There is mean ergodic theorem along many other sequences we know, such as the primes, and the limit is the limit of these exponential sums or Fourier transform of the sequence usually is 0 for irrational alpha. And actually in this talk, we are going to focus on the cases when alpha may not be 0 and see what we get. Okay, so very often I will do this. So I just remind people of the notations up there. So it's nothing more. It has no content because I have a very short memory, especially when it comes to formulas. So here is a definition. So we take a strictly increasing sequence of integers. Sometimes I refer to it as a subset of the integers. And so this is a strictly increasing sequence of positive integers. We say that this sequence is good if for every real alpha, the sequence of Fourier transforms. So, what did I do? What did I do? Oh, okay. So the so the sequence of Fourier transforms. So the average of Sn alpha converges, and it's important that for every alpha we have convergence. Equivalently, the sequence averages of the delta function at Sn alpha converges weakly. And I just remark here that this average of the delta Sn alpha is a discrete probability measure on the torus T. And they will play the fundamental role in our talk. And we denote this limit measure, which is supposed to exist, right? So we denote this limit measure by mu sub S alpha. So here it is. Also equivalently, because this is how we started out with, and this is the last time actually I think I talk about ergodic averages. So by the spectral theorem in every dynamical system and F in L2, the sequence of ergodic averages along the sequence Sn converges in L2 norm. So this is just a reminder of the previous things, and I like to mention that being the weak limit of Borel probability measures on T, mu S alpha is a Borel probability measure on T. So the limit measure is that. Main question: what can this limit measure mu alpha mu S alpha be? That's the simple question. First question: can mu S alpha be any Borel probability measure on T? Well, not surprisingly, what mu S alpha actually can be depends on alpha. The big division, the first big division is the case of rational and irrational alphas, and they are very different. Again, that's not surprising. And that is a result of old result of, well, in his uniform distribution paper. As far as I know, he had only one in 1915. So the Haar-Lebesgue probability measure lambda. So here I introduce this notation for the Lebesgue probability measure on the torus. So the Haar-Lebesgue probability measure lambda of those alpha for which the limit measure is not the Lebesgue measure is 0. So actually we'll be interested in a very small set of alphas, as you will see. So this is still in the subject of main question, but this is some reminder of Fourier coefficients of a measure, because I'm using a little bit different notation, actually a very different notation from the usual one. So for a Borel measure mu on T, on the torus, and continuous function phi defined on the torus, we use the functional notation that u phi is in fact just the integral of phi with respect to that measure mu. In particular, mu of e to the p is the for an integer p is the p's Fourier coefficient of mu. So instead of using the hat notation, I'm using this notation. I remark here that when we look at the Fourier coefficients of the Lebesgue measure, then they are all zero, unless p is equal to 0. In that case, the Fourier coefficient is equal to 1 because it's a probability measure. So by a Weierstrass approximation theorem, so the limit measure is a consequence of the existence of oh, again I pushed the wrong button. Oh, what is this? I'm pushing the correct one. Oh, what did I do? I meant a lot, like this one. Okay, actually even more. So it is a consequence of the existence of these averages of e to the p s n alpha. So we can call this actually the p Fourier coefficient of these discrete measure these discrete measures for every p in z. Note the following, and actually what you really want to note is this is the beginning and the end here. So when we look at the p's Fourier coefficient of the limit measure at alpha is the same as the first Fourier coefficient of the limit measure at p alpha. So, okay. So according to Wiener's theorem, the Borel measure nu on t is continuous if and only if the average of the Fourier coefficients of the measure go to 0. So this is. So again, this is just a reminder of kind of what we were talking about here. So to appreciate the main question, know that for a given Borel probability measure nu on the torus and irrational alpha, we can easily construct a set S, so that the limit measure is equal to nu. Okay, so that's easy to construct. For example, so this can be done in multiple ways. In case of a point mass, for example, that's particularly easy because, so say the point mass is at 1/2, then the construction is particularly simple since all we need is to have the limit of S and alpha be equal to 1/2 mod 1, which can be achieved since n alpha, so the multiples of alpha, integer multiples of alpha is dense mod 1. Right? So this is easy to do. But the important thing here is that we are just taking a single alpha. And so in order to have the difficulty of our problems will be that what we want is a set which is a good set. So we have convergence for every alpha. And in this case, we may not have convergence. Actually, in this case, this is not this the Sn which will satisfy this cannot be a good set. So we will see it in a minute. Well, maybe two. So this is just a definition so that it's easier to talk about this stuff. So representation of a measure. So given a real number alpha and a Borel probability measure nu, we say nu is representable at alpha if there is a good set, important, if there is a good set S, so that the limit measure at alpha, just at that given alpha, is equal to nu. So here I emphasize that the limit measure mu as beta exists for every beta. Okay, so that's a requirement here. Let's look at the case of rational alpha, because in fact in this case the result is pleasing. So in this case now alpha is equal to A over Q in lowest terms, and so the limit measure looks like this. And as soon as you look at how the limit measure is obtained from these averages, you realize that the limit measure is supported on the Qth root of unity, right? So what we see is that the limit measure is supported on this finite set. So for example, since I already talked about the square, so let's single out the primes. So in case of the primes, by the prime number theorem in arithmetic progressions, so we have to use a non-trivial result here. If Sn is the nth prime number, then the limit measure at A over Q is the uniform probability measure on this set. And notice what we have here is those fractions B over Q, where B is relatively prime to Q, because these are the only residue classes where we can obtain infinitely many prime numbers. So that's what we are looking at. And since we are talking about uniform probability measure, so each point here, according to the limit measure, is supposed to have 1 over phi q, where phi q is Euler's totient function, but it's just simply the number of reduced residues mod q. Okay. So again, that's just a notation, repetition of the notations up there. And we have this theorem, pleasing theorem. So if we take any probability measure mu on the Qth roots of unity, and we take any element of T sub Q, then mu is representable at A over Q. That is just a reminder of this definition. So there is a good set S so that the limit measure at A over Q is equal to nu. Okay, so this is a complete resolution of the question, at least for a rational rational number. So obviously the more interesting question is the case of irrational alpha. So let alpha be irrational. This is just a reminder of the various limits and notations. So again, this is just the piece coefficient, Fourier coefficient of the measure, of the limit measure. And so in case Sn is just all the integers or the squares, or we look at the greatest integer part of n cubed times log n, or the nth prime number, then the limit measure for this at this irrational alpha is equal to the Lebesgue measure. It means that all the non-zero Fourier coefficients will be equal to 0. Okay, so this is what we always have, and then limits are nice and such. We like that, but this also ensure also in case of, for example, the anyways, I don't want to say that. Can we get the limit measure to be something other than lambda? Immediately, that's a question, because it's just always lambda for the well-known sequences. Let us try absolutely continuous measures. Okay. So, so let's take a interval, any interval in the torus, and let's take the Borel measure, which is actually the absolutely continuous measure with the Radon-Nikodym derivative being the indicator, the normalized indicator of the interval, right? So what you see is this is the normalized indicator of the interval multiplied by the Lebesgue measure. Okay, so then for a given irrational alpha, let us define this set S, which is just simply those integers n for which n alpha, the multiple of n is n alpha, is in the interval mod 1. Okay, so here is a picture because I am extremely visual. So for example, if the interval has endpoints a, b, and alpha is actually square root of 2 minus 1, although you cannot really see that. But anyways, then we just consider the first 6 multiples of alpha, and those which are in the interval AB, they are considered, and those which are outside are not considered, and that's why they are crossed out with red X. Now, if we write this S as a sequence, so S1, S2, etc., then the limit measure, the limit measure exists for every beta. So in other words, S is a good set. And we can see, not very complicated calculation, that the limit measure is exactly our mu, which was given here. So it's exactly the absolutely continuous measure with Radon-Nikodym derivative being the normalized indicator of the interval. I want to mention that if I replace I, so the interval I, by any Jordan measurable set, we can construct the same good. So we can construct the S exactly in the same way, except that exactly in the same way. So just replace I by a Jordan measurable set. On the other hand, if you take an open set, then in general you are not going to get in this definition, you are not going to get a good set. So that's where the problems begin. So let alpha be irrational, and here we have this theorem by the 4 of us, so Lessing, Anthony Quast, and Joe Rosenblatt, and myself. So for every good sequence S, the limit Borel probability measure mu S alpha is continuous, must be continuous. So for example, it cannot be what we saw before, the Dirac measure at 1/2. It's an impossibility. Okay. So as a consequence, by Wiener's theorem, if we take the limit of the averages of the Fourier coefficients, then the limit will be 0, because Wiener's theorem says that if you take any measure, then the limit of the averages of the Fourier coefficients is related to the atomic measures. Okay. So here we have this actually recent result with Emmanuel Lessing, and myself. So if the Borel probability measure mu is a Reichmann, so Reichmann is the man you saw in the very beginning of the talk. So if the measure is Reichmann, and that means that the Fourier coefficients not in average, but stronger, so they go to 0, then mu can be represented at alpha. Okay, so that's the theorem. And I'd like to emphasize here that Reichmann measure can be represented at every irrational alpha. So I just want to re-emphasize that. Of course, the good sequence, the good set will depend on alpha, but nevertheless, we can have this representation. And I also want to tell you that if we take any measure which is absolutely continuous, then it is Reichmann by the Riemann-Lebesgue lemma. Okay, so this includes that, but this includes plenty of singular measures. So what's going to happen with non-Reichmann measures? For example, the uniform measure on the contour set. So here we have this theorem by the 4 of us, so Lessing, Quast, Rosenblatt, and myself. So if the Borel probability measure nu is non-Reichmann, then there is a set A with Lebesgue measure 1, so that nu cannot be represented at any alpha. So that's a striking contrast to Reichmann measures. They can be represented at every single irrational alpha. So we have a 0-1 law. I don't know if we can call it that way, but it sounds actually good. So Riemann probability measures can be represented at every irrational alpha. So on a set A, where in particular, which has Lebesgue measure 1, while non-Riemann probability measures can be represented on a set A with 0 Lebesgue measure. And this, or could, I should have said maybe could be represented, because it's a possibility that maybe is empty. A is empty, is the empty set, which means that continuous measure cannot be represented anywhere. So that's a possibility, and we don't know whether that's the case. But in case you wonder whether there are any non-Riemann measures which can be represented, so again, it's a very recent result, so 2022 result of Cuny and Parot. There is a good set S and an irrational alpha, so it has to be found carefully. So there is a good set S and an irrational alpha, so that the limit measure is non-Riemann. Okay, obviously it's a singular measure, and it's non-Riemann. It's a little interlude, because when you think about lots of possibly different limit measures, then I think some of us would think about the Wiener-Wintner theorem. And in case you are not familiar with that, so the Wiener-Wintner theorem says that if you take any dynamical system and E is a measurable set, then the limit of these averages, right? So this is just the usual ergodic averages for the indicator of E, but it is multiplied by E of n beta, exists for almost every x and every beta. So in particular, if let's just look at this. So if T is ergodic and the measure of the set is greater than 0, then for almost every x, the set of n's where T and x enters the set E is a good set. Okay, so this is a good set. Now, so what is this limit measure in this case? Well, I don't pretend to find it out, but here is what we can say about that. So if T is ergodic and the measure of E is greater than 0, then this set S, so this set S has positive density for almost every x. And so, and actually this density, well, then that density is exactly this average, right? The limit of these averages, and the density is equal to the measure of the set. It's not difficult to see that then U as beta is absolutely continuous with respect to lambda for every beta. So in particular, it is Riemann. Right? So the Wiener-Wintner theorem is not going to produce us any new measures which we can already construct, well, in quotes, construct in a theorem with Emmanuel. Okay, so actually the situation is even more restrictive, because in case of a set with positive density, then not only the limit measure will be absolutely continuous, but the Radon-Nikodym derivative of the limit measure with respect to the Lebesgue measure is a bounded function. Okay, so as soon as you take a limit measure which may be absolutely continuous, but with unbounded Radon-Nikodym derivative, then the good set must be of 0 measure. So that's mentioned that. So what are the remaining questions? I started at 45. I forgot 45, right? Okay. So yeah, but this is good. I think I am good. See how done I am. I am already there. So which continuous Borel probability measures can be represented at some irrational alpha? That's the remaining question, right? And so we have some answers, but clearly we don't have all the answers. Let me say this. So if the continuous Borel probability measure nu is invariant with respect to multiplication by both 2 and 3, and mu is not the Lebesgue measure, then it cannot be represented at any rational alpha. And actually, yeah, okay. So if you, for example, if you looking at the, I don't know what the logical term for it is, that, so if you look at kind of the converse, so if you say somehow you figure it out that every continuous measure can be represented at some irrational alpha, then that means that any measure which is invariant with respect to multiplication by both 2 and 3 must be the Lebesgue measure, and that would be Fürstenberg's conjecture. Oh, I even say that. I forgot. I forgot that time. I think, yeah. So yeah. Anyways, so I just said that, right? I forgot that I wrote it down there. Now, I also want to say that once you are given a continuous measure, then it's not like potentially there is a magical alpha which will represent any continuous measure. So maybe that could be your idea. Actually, for a long time, that was my idea. You know, we take, for example, the golden mean. I mean, it is such an amazing alpha. It distributes so well, so probably it will represent any continuous measure. But here we have this fact that there is no magical alpha where potentially every continuous measure can be represented. For every irrational alpha, however nice you think it is, there is a continuous measure which cannot be represented at that alpha. So I just wanted to say that. In other words, if you are given a continuous measure and you try to represent it, you have to mine alphas in an already zero measure, Lebesgue zero measure set. Remaining question, because notice that so far we concentrated on a given irrational alpha, but what's going to happen with the limit measures for all the other alphas, because the limit measures exist for every single alpha, right? So that's the question. And I can say the following, that by the easier direction of Lyon's characterization of Reuchmann measures already observed by Reuchmann. So this easier direction for every good set S and Reuchmann measure nu, the mu measure of those alphas where the limit measure is not the Lebesgue measure is zero. So in particular, since the Lebesgue measure is Reuchmann, so we get the well-known result of Wierdl, that the Lebesgue measure of those alphas where mu s alpha is not the Lebesgue measure is zero. So I just want to make some remarks on the proof. I'm not going to get into the proofs at all, just what kind of proof we have. So first we need a definition. So we say that a sequence of real numbers W is a weight if it's a non-negative sequence. So for every n, Wn is greater or equal to 0. And this is just a notation. For a given non-identically zero weight, the W-weighted average is this. So this is kind of the same kind of notation what Florian was using, right? And this is, and we are given a sequence of numbers or even elements of a Hilbert space. Then the W-weighted average is this. So we are taking the weighted sum of the FNs, and then we divide by the sum of the weights. Right? So this is just that notation. And I use this notation because on the next slide I need it only once. I'm sorry for introducing such a notation like that. So let alpha be. So what proof are we talking about? I'm just repeating our theorem with Emmanuel. So let alpha be rational if the Borel probability measure nu is Reuchmann. meaning again that the Fourier coefficients go to 0, then nu can be represented at alpha. So there is a good set S with the limit measure being equal to nu at alpha. Okay, so that's the, and so I just want to make a few remarks on the proof. So what we do first for a given Riemann nu, we first construct a weight W, so that the W weighted averages converge to mu. And how do we do that? Well, I mean, I think it's not a particularly simple argument, but the essence of this is that we use the Feyer kernel for the Fourier series of the measure, which is kind of strange. But anyways, that's what we do. So we use the Feyer kernel for the Fourier series of so what we do is we take the arithmetic average of the partial sums of the Fourier series of the measure. That's what we do. And in this way, doing some manipulation, we get a weighted sum. So we get a weighted sum of these delta measures. So this is the W weighted sum. And we find that for every beta, this limit exists. And the limit of these weighted averages will be the chosen measure nu. So we can say that this weight is a good weight. It's not a good sequence, it's a good weight, right? So now how do we get the good sequence? So we then randomly construct. Actually, Ruja always uses construct. So I can use, well, not always, but I heard him doing it many times. Then he apologizes. So we then randomly construct a good S, which represent mu at alpha. That is mu S alpha. So the limit measure is equal to mu at alpha. And how do we do that? Well, we use W as expectation. So what we do is that we show that almost every set S satisfies right? So what we do is we look at the average along that random set. Sn here is actually the initial segment of the set S. So that's what it is. So and that's what we average over. So these random averages are compared with the W weighted averages, which we already know converge to the right thing for us. Okay. So and the good set S representing U can be taken to be a subset of your favorite set. The set of squares, primes, or randomly generated set, many other sets. Actually, we have very little restriction. That the measure is what? Right? Yeah, exactly. And yeah, so as Emmanuel said, and he told me many times that I should not forget to emphasize this. So it's very important that our set is a good set. Okay, so this randomly generated set at the end. So what we have is that the limit measure exists for every, so mu S beta exists for every beta, and at alpha we get the mu. Okay, so because as I said in the very beginning, it's easy to construct a set where the at a given alpha the limit measure is equal to mu. The important thing is that we have a good set. Okay. So yeah. So then it just means that for example, when we look at the weighted averages, in case of the we want a S which is a subset of the squares, you replace here the n by n squared. That's all you do. I mean, meaning that you have to have an argument, but what I'm saying is the argument has exactly the same scheme as what we used here for a subset of all the integers. And so I think actually I stop here, but on this slide I give you the argument because I think it's pretty interesting. So let me just say this. Yeah. Well, but I don't want people to be late from places. But anyways, so so let's say that alpha is irrational and mu be a continuous Borel probability measure, which is invariant with respect to multiplication by 2 and 3. And so suppose that for a good set S, we have that the limit measure at alpha, at our given irrational alpha, is equal to mu. So then mu is the lambda measure. It must be the Lebesgue measure. And I cannot finish in 2 minutes, I think. Well, I don't know. It would stretch it. So I just put it up. Well, it's there. You can. So the thing is that so you give an indirect proof. So suppose that mu is not the Lebesgue measure. So then it means, by definition, then it means that there is a non-zero p, so that the p Fourier coefficient of mu is not 0. So since mu is assumed to be times 2 times 3 invariant, for every jk we must have that this Fourier coefficient. So the p times 2 to the j, 3 to the k Fourier coefficient is they are all equal. Oh, what did I do? Yeah, no, I have to go forward because this is my last slide. So they all equal to the same thing here. They all equal to the same thing. Now notice we talked about this, that actually this Fourier Fourier coefficient, so the p times 2 to the j 3 to the k Fourier coefficient, is equal to the limit, the first Fourier coefficient of the limit measure at p times 2 to the j 3 to the k alpha. Okay, so notice that. Now, by Fürstenberg's theorem, because he has a related theorem to all this, we know that this set p times 2 to the j 3 to the k alpha, where j and k run through all the integers, is dense in the top. So we know that. So in particular, when we look at the absolute value of the limit measure, the first Fourier coefficient of the limit measures, then it is equal to the p Fourier coefficient of nu, which we just assume to be greater than 0 for a dense set of betas, right? So this is what we get by Fürstenberg's theorem. Now, namely, what are the betas? Well, you can see it here. So my finger is too big, I guess, or something. It's not that big. And so namely, the betas are this, which is a dense set. First Fourier coefficient is equal to 0, on the other hand, for a dense set of betas as well, as a consequence of Weil's theorem. And now if we define phi beta as the absolute value of the limit measures at, so the first Fourier coefficient of the limit measures, this function exists for every beta, and it is a limit of continuous functions. But this is a constant at a dense set, and it is 0, non-zero constant at a dense set, and it is 0 at a dense set. That's impossible for a limit of continuous function. So I did it apparently. Actually, that's exactly the kind of measure you Cuny and Parot construct. So the limb soup of the Fourier coefficients on a set, not even that, it's a limb soup, in fact. So the limb soup of the Fourier, the absolute value of the Fourier coefficients is equal to 1. And in fact, they are asking whether there is some kind of construction where the link soup is not one, but something different, because at least their construction certainly doesn't give that.
The next talk resumes after 2 minutes at 11:35.